we were mostly involved. So I will start. We also have some students here. So with an introduction about the reason why we need indirect methods in nuclear astrophysics. I will introduce also the Trojan Horse Method, and then I will present 4, very briefly, scientific cases. Okay, so when we are studying reaction of astrophysical interest, the problem is that besides the fact that inside the interior of the stars we have a very high temperature, in the case of the sun it's 15 million Kelvin, once we think about what is the average kinetic energy, we go down to the tens of hundreds keV region. So it means that since we have a reaction between charged particles, we are far below the Coulomb barrier. And this suppresses a lot the cross-section of the reaction. And of course, we can perform on Earth, let's say, regular experiments, as we are used to perform. We can decrease the energy up to some point. And then, of course, the cross-section is too small. We can maybe run a longer experiment, but then we are somehow to face the problem of the background, which is also increasing linearly with the duration of the experiment. So it's very easy to enter the region where we have to perform to make some extrapolation of the cross-section. So a very convenient way to perform this kind of extrapolation is to factorize the cross-section in terms of a geometrical term, this 1 over E, then to put all the Coulomb suppression factor inside this factor here, and to leave all nuclear physics inside the astrophysical S factor. In this way, we have a more linear, somehow, behavior of this parameter, and we have less dangerous extrapolation when we go to the range of astrophysical interest. However, there may be some resonances that we miss in this region. We might have the tails of some subthreshold resonances. So that's the reason why it's also important to have indirect methods that can provide us a way to access this very interesting part. Another problem that we have to face when we perform this experiment at very low energy is the screening, which is produced by the electron cloud. Okay, in the stellar environment, the reactions are occurring, and so we don't have electrons that are bound to the nuclei, but we have a sort of a sea of free electrons. So we need this plasma somehow potential to take into account. In our experiment, so at first we have to make some extrapolation to get this plasma potential, and it's much more convenient to start from the bare nucleus potential in between the nuclei. However, when we perform this experiment, it's very common to have a fully stripped projectile, but the target will always have all the electrons surrounding the different nuclei of the target. Therefore, we have a screening of the repulsion in between the bare nuclei, and therefore, from direct measurement, what is extracted is the screen potential. Then we have to make some approximation in order to extract the bare nucleus potential, and then to go to the plasma configuration. Therefore, in the case of measurements performed with the indirect method, since projectile and targets will be, let's say, fully stripped, we can reconstruct immediately the bare nuclear potential. So indirect methods, and we have a series of them, and Trojan Horse is just one of them. So as you can see, they give us the possibility to explore and to reach regions of energy below the standard limit that you can achieve with direct measurements. So you don't have the Coulomb suppression effect. We will see the reason why. Then we can get independent information of the screening potential, and also we can overcome technical difficulties in producing either the beam or the target, because we might have reaction, or we might be interested in reaction induced by radioactive ions or in neutron-induced reactions. Of course, being experimentalist, everything, as in normal life, comes to a sort of a price. In this case, the problem is that somehow we have to relate the cross-section that we measure to the cross-section we are interested in with reaction theory. But anyhow, after many decades of this kind of studies, this is a well-established technique. So in this case, for instance, we are interested in the reaction between particle X with particle capital A within the exit channel small b with little b with, let's say, capital B. So this is the reaction of astrophysical interest. And of course, we have to compete with the Coulomb potential in between particle X and particle A. So the trick of the Trojan horse, like in Greek mythology, is to hide particle X inside the Trojan horse nucleus, which is particle A, which is composed, so it has a very well-pronounced structure as X plus S. What's the reason of S? S should be just a spectator in the reaction. So the reaction should be performed under the kinematical conditions that are ensuring that this particle S is not participating in the actual reaction. The advantage are that there is no Coulomb suppression because essentially particle S is brought inside the Coulomb field of particle A already, inside the projectile A, and then we have the breakup of X plus S, and then there is no electron screening because we are already somehow inside. And okay, this reaction has been used already for more than 30 years, and it's been applied to more than 30 reactions. There is a relationship between the three-body cross-section that we measure to the two-body reaction of interest, and there is a proportionality that takes into account the momentum distribution of particle S. Of course, what is a typical Trojan horse nucleus, for instance, is deuterium, with, of course, a very well-pronounced structure as P plus N, or helium-6 as alpha plus D, or we will see in the case of the carbon-12 experiment, even nitrogen-14 as carbon-12 plus D was used as a Trojan horse. So we need to know what is the momentum distribution of the spectator inside the Trojan horse nucleus, and then we have a kinematical factor which is typically reconstructed using a simulation. Then what is also in this case the price that you have to pay, that here you don't have an equality sign, you just have a proportionality. So it means that you need to normalize the data to some already existing measurements, but since you are not just performing a measurement at a single energy, in the sense that you have the same projectile energy, but then when you have the breakup of the projectile into X plus S, you have a continuum spectrum of energies, so you can extend your measurement of the two-body cross-section even, and you can cover the range which has already been covered in the same experiment with the same beam energy already covered by direct measurements. So in some way you have to normalize to already existing measurements. And okay, here we have the summary or just the review of the different measurements. The first one is the carbon-12 fusion. For those that are not very familiar with nuclear astrophysics, we know that in stellar evolution we have different stages. At first, the star is burning hydrogen, like our sun. Then we pass to the second stage, which is helium burning, red giant stars. And then, if the star is very massive, can proceed and start burning carbon, then neon, then oxygen, and so on, finally approaching the core collapse supernova and the final explosion. So to reach this third stage of the stellar evolution, it critically depends on the initial mass of the star. And this value critically depends on the astrophysical S factor for the at zero energy for the carbon-12 plus carbon-12 measurement. Direct measurement, they stop around 2 MeV, center of mass energy, and the region of interest is, as you can see here, below 1 MeV, between 1 and 3 MeV. And there are also some technical difficulties because when you study carbon-12 on carbon-12, you might have even a little isotopic contamination of the carbon-12 target with a minimum concentration of carbon-13. And of course, you have to take into account and to purify your target. And is a sort of holy grail for people that are interested in nuclear astrophysics. In this case, so the reaction was studied with, and we will see in the coming transparencies, with the reaction. The experiment was performed at Catania, so at LNS. The beam was nitrogen-14 on a carbon-12 target. And in this experiment, so you look at the reaction carbon-12, you produce excited states of magnesium-24. And here the complication is also due to the fact you are, let's say, with a lot of states in the same, within the same, in the energy range of interest for astrophysics. And the main contribution are coming from two channels. This channel here, the alpha neon 20, and the other channel is the proton sodium 23. So in this experiment, they measure the coincidences between these two particles, and they measure 4 different channels, the so-called alpha 0, which is the one that leaves neon 20 in the ground state, alpha 1, which leaves neon 20 in the first excited states, and P0 and P1 with a similar nomenclature for the channel with, as the other partner in the reaction, sodium 23. And okay, here you can see, according to the new measurement, that as you can see here, according to the R matrix calculation, sorry, I have to go back and forth, was able somehow to cover also this range and to make some predictions also about the strength of these resonances in this range of interest. And as you can see, compare, once you insert this reaction rate in the proper code, you can see the differences with respect to the previous code, CF88. The same reaction might be interesting in different astrophysical scenarios, so in the explosive burning or hydrostatic, so the quiescent burning, or for the super burst, depending, of course, on the temperature. This is the scale of the gigakelvin, so it means billions of Kelvin. And you can see that at 1.2 gigakelvin, when we are here, there was an increase of 18%. But for the super burst, so at 0.5 gigakelvin, the increase was even a factor 25 compared to the previous reaction rate. Okay, this is still the former version of the presentation. So, well, in the new one, I was skipping this part, not to be too long. Another experiment that was that we performed and that we studied was performed at our facility, Exotic, in Legnaro. And in this case, we were interested in looking at the reaction beryllium-7 plus neutron with, in the exit channel, alpha plus alpha. And this measurement is important for the cosmological lithium problem. So this is the network of the reaction of the Big Bang nucleosynthesis. So we are not in the stellar revolution, we are just in the early minutes of the universe, and these are the first nuclear reactions that occur somehow in the history of our universe. So the end products of the Big Bang nucleosynthesis are, okay, protons, which were available already since almost the beginning, then helium-4, deuterium, helium-3, and also little concentration of lithium-6 and lithium-7. Everything agrees somehow with the model for what concerns helium-4, deuterium, and helium-3. When we look at the lithium-7, there is a discrepancy of a factor of 3. So what we expect is much larger than what is observed in metal-poor stars, which should be, let's say, the most ancient stars that we can observe in the sky. So what could be at the reason why we have less lithium-7 than what we expect? Since lithium-7 is essentially produced by the beta decay of beryllium-7, if there are some parallel destruction mechanism of beryllium-7, like for instance the beryllium-7 alpha plus alpha reaction, if this cross-section is larger than what we know or we extrapolated, in principle we can, to some extent, try to solve or to provide a sort of nuclear physics solution to this cosmological problem. So the experiment was performed at Legnaro, at our facility. So we used the beryllium-7 radioactive avion beam on a deuteron target, which was a plastic target, so a CD2 target properly deuterated. The proton was a spectator in the reaction, and we measured the coincidences between the alpha particles. To make sure that the proton, which was undetected in our experiment, was simply a spectator, in planning the experiment, different, as you can see, this is the plot with the theta angles for alpha 1 and the theta angle, so the polar angle for alpha 2, with different gates on the momentum of the spectator. So in black, almost the full momentum of the spectator. In red, up to certain unit, so 30 MeV over C. And then for even lower momentum, or linear momentum of the spectator, so 10 is the blue points. So we put our detectors exactly at this angle in a symmetrical configuration in order somehow to maximize in the experiment the probability to have a quasi-free reaction mechanism. So here is a picture of the experimental setup. We used delta E identification technique with ionization chambers as a first layer, and then we have DSSD detectors, so solid-state detectors made by silicon with a double-sided, so in order to achieve a pixel configuration of 2 × 2 millimeters. And just some examples about the particle identification, the reconstruction of the Q value, and the comparison between the simulation and the experimental data, just to give you an idea about the fact that we were able somehow to reproduce or at least, let's say, to magnify the effects related to the quasi-free scattering, quasi-free mechanism, and that everything was in the energy range where we were expecting. Okay, here we are comparing the relative energy between the 2 alpha particles with the relative energy between an alpha particle and a proton. Here you see a large concentration of data that corresponds to the population of an excited states of alpha plus alpha, so an excited states at 16.9 MeV of beryllium-8. Here there are no horizontal lines, so it means that there were no resonances of lithium-5 alpha plus P produced in the reaction, because kinematically we look at coincidences between alpha particles, but we do not know what is the origin, because there may be a sequential mechanism producing lithium-5 in between. So in the data analysis, we have also to make sure that there are only, in a similar plot, only vertical lines and no horizontal lines. Otherwise, of course, you have a source of background which is larger in your measurements. And here we have again, the relative energy between the 2 alpha particles, so related somehow to the excitation energy of beryllium-8, as a function of the momentum of the spectator. So you see here, again, relative energy as a function of the momentum of the spectator. Opla. And here is the population, and we can, if we divide the 3-body reaction cross-section by the kinematical factor, if you remember the formula which was shown previously, we can extract the momentum distribution of the spectator. And we can compare, so the momentum spectator, in this case of the proton, with the Hulten function, which is the momentum distribution of a proton inside deuterium. As you can see, everything is in arbitrary units, but anyhow, the shape of this distribution compares rather well with the Hulten function. So this means that the events that we selected are those that are compatible with a quasi-free mechanism, because the momentum of the spectator is essentially the same as the momentum of the same particles inside the Trojan horse nucleus. All this story just to say that our points, which are the blue one, are essentially confirming the trend of the previous measurements. So we are not able to provide a nuclear physics solution to this cosmological problem. So somehow the reason of this discrepancy has to look in maybe the early stages of the stellar evolution, so just at the formation of a star. Just 2 brief words about other work where we'll be involved. We had a PhD student from the Beiyang University in China. She spent 1 year in Padova, and she was analyzing the data of an experiment, fluorine-17 plus proton into oxygen-16 plus alpha in the exit channel. And she's close to get the final results of these analyses. Fluorine-17 is a monoisotopic element, very fragile, so is sort of fingerprints to test different astrophysical models for different astrophysical scenarios, especially for asymptotic giant branch stars. In this case, as you can see, there is the red data, which are corresponding to the population of oxygen-16 in the ground state, and there are measurements, direct measurements, and also a Trojan horse measurement. They are in agreement with each other. And then there was a publication 3 years ago about the alpha-gamma. Alpha-gamma is the way that historically is given to the alpha-2, alpha-3, and alpha-4 channels, which are then decaying towards the ground state via gamma emission, while the alpha-1 is called alpha-pi, because it's a 0+ state, so it cannot decay via gamma transition towards the ground state. So it's a little bit confusing, but anyhow. So what was important of this measurement performed at the Juna laboratory in China? They measured the alpha gamma in a direct way for the first time. And as you can see, their predictions, according to the R matrix calculation, are the population of these resonance very close to the threshold at 11 keV. So again, this experiment with the Trojan Horse method was performed in Catania, and it was somehow tailored to measure not the ground state, but the alpha pi, and also the alpha 2, alpha 3, alpha 4, so alpha pi and alpha gamma. So this is just a result obtained over the last weeks by Xedo, and you can see that this state at 11 keV is observed also in our analysis. Now she's working at separating the different peaks with a Gaussian fit and taking into account also the non-resonant part, the angular distribution, in order to get the resonance stress of all the states. However, we also have the confirmation from this indirect measurement of the population of this very important state just at 11 keV. And okay, this is the activity where we are involved with a master student. This is an experiment that we tried 2 years ago in Triumph, and probably it will be repeated, it should be repeated in July this year. And this is related to the destruction channel of aluminum-26. Aluminum-26 is also a very important nucleus for astrophysics, and the reason is related to its half-life. The half-life is 700,000 years, which compared to our lifetime is extremely long. To compare to the time scale of the, let's say, stellar processes is rather short. So aluminum-26 decays in magnesium-26 to an excited state, emitting a gamma ray of 1.8 MeV. So whenever you observe this gamma ray in the sky, it means that it's a region that has been active according to the nucleosynthesis recently in astronomical times. So there are different predictions, and I'm running out of time. So we want to investigate the neutron destruction channel of aluminum-26. So the experiment is planned. Our student is working somehow at the detector calibration and developing all the software which is needed in order to speed up the analysis later on. I hope he will become also a PhD student in the next years. And in principle, we want to detect the proton with the detectors that are close to the target. This is the beam direction, and the heavy fragments at very forward angles. It will be complicated in this case by the fact that the proton is the participant to the reaction, and the other proton is a spectator. So it will be a little bit more time consuming, the data analysis. And I'm just coming to the summary. So I hope within my knowledge to convince you that nuclear physics is a fundamental pillar of nuclear astrophysics, and we can also can contribute with our experiments. Indirect methods are very unique tools to investigate reaction on energy ranges difficult to access in that direct way, and there is still a great potential for future applications. So thank you very much for the attention.
Question, please. Any question?
About the carbon 12. No, just about the carbon 12 plus carbon 12. There, is that the final story, or there were some follow-up about?
Okay, there are some slides that I removed. I needed to make a phone call to Aurora over the last days, but she was in Strasbourg for an additional meeting. So it's not the end of the story.
I see.
For sure. She would have spoken much longer about this, this part for sure in her contribution, so my apologies, yeah. But it's not the end of the story.
Have you obtained the precision that you were looking for in this measurement, or not yet?
Actually, I know that I think in 2019, because it was before COVID times, in a similar way also the experiment oxygen 16 plus carbon 12 was studied, and also the same reaction was repeated but at higher energy, in order to have some additional points in order to fit a little bit better where we have to perform the normalization of the data. But
yeah, okay.
Unfortunately, I mean, I cannot answer more precisely.
Any other
Okay, thanks to you.
The next speaker is Patrick O'Malley from the University of Notre Dame, USA. This is Helium 48 up to calcium 48 measurements to constrain the statistical rate of Helium 47.
Yep.
If I remember how to do a slideshow. Someone quickly remind me how to put this in a slideshow. Control it. Nope. This is okay. Sorry. Hello, everyone. I just want to take a second to thank Athena and the organizers again for inviting me out to this very nice conference. Very nice area. I've been wanting to visit since Athena's been collaborating with us, but haven't had the chance yet until now. So I wanted to take a minute to talk to you about a new system we've installed. Well, I say new system we've installed at Notre Dame. This is actually the work of grad student Scott Carmichael mostly. Talk about the split pole spectrograph we've installed and how we're using it to constrain the 57 nickel P gamma reaction. So in nuclear science today, one of the big questions we're trying to answer is to understand the origin of elements in the universe. Now, different stellar sites have different, more exotic reactions that occur, but for our purposes, we're going to focus on nucleosynthesis that occurs in core collapse supernova. Now, for the students in the audience, for stars that are at least 8 times the mass of the sun, they eventually get to the point in their stellar life where they're essentially left with an inert nickel core with a series of different shell burnings that occur as you go further out. Now, eventually the star will get to the point where the mass of the core is so heavy that it's able to overcome the Coulomb force and compress towards nuclear densities. And when it happens, you get this, the outer layers continue to expand and the core collapses, but then rebounds, slamming into the expanding layers, causing an increase in heat and density, which allows certain nucleosynthesis reactions to occur, particularly alpha-induced reactions. Now, after this occurs, during the injection phase, there are certain nuclei that have characteristic gamma rays that are important, because we can observe those after the fact, and it'll help us give us some information about what happened during the core collapse supernova. In particular, titanium-44 is something we can observe now in the ejecta. So if we want to understand better cosmic core collapse supernova, we need to understand the reactions that produce and destroy titanium-44. Now, a paper back about 10 years ago from Mazzocco that all demonstrated that nickel 57 P gamma actually had a significant effect on the production of 44 titanium. And then 10 years later, Hermansen et al. Also confirmed this effect and also showed that nickel 59 production would also be affected. Now, nickel 59 is another one of these isotopes that has characteristic gamma rays that would be produced during core collapse supernova. And the next generation telescopes, when they come online, will actually be able to identify these. Now, since nickel 57 is radioactive, there's no current direct data available for this. So all the reaction rates we have for this are theoretical. Now, in these high temperature environments, the rate is normally dominated by compound resonances through excited states in carbon-58. In our temperature region, we're mostly interested in this 3 to 6 MeV excitation area. Now, currently, all of our theoretical rates are based on Hausser-Feshbach formalisms. But you can see from this list of levels, the level density isn't really high enough to support a good Hartree-Falk extrapolation for the reaction rate. So in this sort of environment, what you prefer is to use the narrow resonance formalism. But to do so will require precise determination of level energies, as well as proton gamma valency ratios, spin parities of all the states in copper 58 in order to get this reaction rate from these. And before we try to proceed with any kind of radioactive experiment, what we really need to do is try to understand the structure of 58 through other means. Now, it's just brief review. So we want to understand the nucleosynthesis occurring in compound core collapse supernova. So we need to understand how 44 titanium is produced. To understand how 44 titanium is produced, we need to constrain the nickel 57 p gamma reaction rate. And in order to do that, we need to understand the structure of copper 58, and particularly in the level energies in the 3 to 6 MeV excitation area. Now, at Notre Dame, we inherited a free spectrograph from Oak Ridge when it closed down a few years ago. The nice thing about a spectrograph is, as a magnetic spectrometer, it focuses particles with the same rigidity to the same place on the focal plane. Now, what this does is allows us to kind of translate position into energy, which actually allows us more precise determination, better separation of energy levels through position. In particular, the split pole design gives us a second order focusing effect at the focal plane and gives us some vertical focusing as well, which actually increases our overall angular acceptance. And at the INGI we've installed at Notre Dame can be rotated between 0 and 60 degrees, giving us a good measure of angular distributions. So just to give you an idea, this multi-ton system is basically just one little detector that we can rotate around at different angles. Now, the installation process unfortunately began in early 2020, and we all know what happened that year. So it ended up taking much longer than we had hoped to install this thing. Just going from here to here, just getting the plat and putting the first platform was about a 2-year process. And unfortunately, Oak Ridge also left the magnet sitting in the parking lot for a year and a half, just in the nice weather of Tennessee. So once we got it, we spent about a year just getting the rust and mold and mildew off the thing before we could put it all back together again. It was very unfortunate. But it's together now, and it works beautifully. So among the components in our system, we've created a position-sensitive ionization chamber, which is installed at the focal plane. Behind it, we'll have a plastic scintillator, just to measure the total energy of whatever punches through the ion chamber. And then in the target chamber here, we'll also surround us with an array of silicon diode detectors to detect the particle decays from the residual nucleus that we populate. Now, the focal plane detector is based on the Yale design, if you're familiar with that. It's comprised of basically a cathode and 2 anode wires. The anode, and then above that is a pad plane. Now, when the anode wires collect the charge, they induce charge on the pad plane itself. Now, each of these pads is separated by a delay line circuit. So we can compare the induced charge on either end and the time between them to effectively get our position determination. And by using our new Mesitech digital DAC, we're able to get a position resolution of about 2.5 millimeters. And here you see a picture of the various delay line circuits. Now, in the target chamber itself, we're going to surround this thing with an array of these little cheap diode detectors, which we can use to, again, look for the decay particles to give us an idea, help us constrain the particle branchings from the states we populate in copper 58. Now, this measurement we tried to do is the first measurement we've done on the INKI, was done back in February. We had a 21 MeV beam of helium-3, about a 40 particle nanoamps. We bombarded a isotopically enriched nickel-58 target. And our goal, again, was to kind of probe the structure of copper-58 in this region. Now, as is always true in modern physics, the states we're interested in were not the most populated states that we want. That's just how it is. But thankfully, with our position-sensitive ionization chamber, we actually get particle ID from position and the cathode. So again, in an INGI, the position directly corresponds to total energy, the position at which it hits on the focal plane. So in this plot, I've plotted the time difference from the left and right. And so the right will be the higher energy particles, and to the left will be the lower energy particles. And you can see we've kind of separated the different species that are coming through. Here we have deuteriums and our alpha particles. And then this group here, kind of cleanly separated from both, is our tritons that we're interested in. The alpha particles actually produced a nice calibration point for us through several known channels. Oh, nice programmed in. Geez, Scott. Okay. So by getting all those tritons and then plotting, doing a background subtraction, and pulling out the excitation spectrum from our position spectrum, we get this, our triton excitation energies. Now, some of these were known before. The gray lines represent previously known states. But there's also several states that haven't been measured before, particularly in our higher energies in our region of interest. And we were able to measure this for several angles, but this is about as far as we've gotten with this analysis so far. But Scott is a go-getter. He wasn't satisfied with one or two thesis projects. He wanted to do another measurement. So at Argonne National Lab a couple of years ago, we did the same measurement using the GODDESS system. Now, for those who aren't familiar, GODDESS is sort of a 4-pi silicon detector array surrounded by a 4-pi germanium detector array. So these germanium detectors are clovers, segmented crystals, which is nice because you're able to get a precise position determination for the gamma ray, which of course later translates into better gamma ray energy resolution due to the increased Doppler correction. Now the silicon array, again, it was a 4-pi silicon array with telescopes at all the forward angles on the forward BB10s and then the forward triple Qs. Now, if we wanted to run at the same kind of intensities that we ran at Notre Dame, but 40 nanoamps of helium-3 would have completely dominated our detector with just elastic scattering rate. So we actually put an aluminum shield directly in front of our forward angle detectors to block the helium-3 that's coming through, which worked well, except that it also absorbed about half the energy of the tritons. So we have severe energy struggling occurring too. But the main goal of this was actually to get the gamma rays. So even with the straggling, we're able to get a nice clean triton plot from our silicon detector arrays, so we can cleanly separate events related to triton production from those from the deuterons and protons. Now, if we take this tritons and gate on our total gamma ray spectrum, we're able to plot a nice gamma ray spectrum with a series of mostly cascades. Most of these are from known states that we're known about. However, what we can do is we can also take our triton gated energy spectrum and plot it versus the triton excitation energies. And we see several lines pop out that were from known levels, but there's also a few that had never been observed before. In particular, this one here, this 2665, is a new gamma ray that hasn't been seen in previous measurements. And if we gate on that gamma ray and project out other coincident gamma rays, we see another gamma ray that occurs right around 411, which gives us evidence of a new level at 3109 that no one has previously seen before. Now, if I go back and look at our spectrum from our ENGI data, we actually see this peak right here very weakly. But this is just from one particular angle. But you see, the reason we use both measurements is that this is our triton excitation energy spectrum up here. If we try to get an angle distribution just from that, we'd have a hard time getting any kind of reasonable resolution from this, even if we gated on the gamma rays. But by combining these two methods, we can get spectroscopic information, spin parities from our ENGI measurement at Notre Dame, but we can also get precise determinations of gamma rays and energy levels using the GODDESS setup at Argonne. So coupled together, we should be able to extract all the information we need to do a nice reaction rate calculation. So in summary, we want to understand the production of titanium-44 and nickel-59 in compound core crop supernova. This reaction rate, this reaction rate isn't certain because it's never been experimentally measured before. So certain information is needed about levels of carbon-58. We used the helium-3T reaction both at Notre Dame using the ENGI and with the GODDESS setup at Argonne National Lab to get level energies, proton branching ratios, gamma branching ratios, and help constrain the spin of certain levels. Once this analysis is all complete, we'll throw this into a prism nucleosynthesis calculation and hopefully investigate how the new rate will impact the production of carbon, titanium-44 and nickel-59. All right. Well, I thank all of our many collaborators on this project, and in particular, Scott Carmichael, who's the grad student doing most of the grunt work on this. All right. Thank you.
Question, please?
How you make the readout of this Aruba?
The readout?
The readout, yes. You have the, it's
Painfully.
also make, but yeah, it's huge.
So we,
It's-
for the first time, this is the third campaign with the GATA system. The first couple of times we tried using their digital system, which was a mess. So in the end, we actually coupled our analog system to their digital system and made the digital system a slave to the analog system, which was a headache for programming, and especially in the reconstruction of the events. But in the end, we actually were able to get a nice, cleaner, more reliable extraction of the data.
Are strip detectors, right? Or
Yeah, there's silica strip detectors. There's
So,
1,028 channels, I
many
believe,
channels,
and then
yes.
2,000 channels of germanium electronics. It's 60 terabytes of data. It was taking a long time
The
to
spectra
analyze.
is amazing. I mean,
Yeah. It's a very powerful system. If you ever get the chance to work on a GATAS experiment, I highly suggest it.
Yes. Yes. So I have a question regarding the charge exchange reactions you have performed, because these reactions are very selective of particle Hall excitations, and typically if you measure at very forward angles, you only see 1+ states or so, 2- at the most.
Sure.
Which is maybe not the complete data set of states that you need, that you can assess by proton on
Sure.
nickel 57. So how you, merge the two? You will only have a partial information from that.
So
yeah?
for the INGI, we did mostly forward angles, scanning from 10 to 35 degrees in various steps. But for the GATAS setup, we actually had 0 to 180 degrees. We had the full, so we have the tritons identified for the full array, for the full angular range. So from that, in principle, we can get information at all angles, right? So we would still get some of the information. Now, it would be entirely a complete picture, but it should give us a lot more spectroscopic information than we currently have.
Other question, please? Okay, if there's no question, thanks again. Okay, the next talk is from Àngel Sànchez-Benìtez from the University of Huelva, Spain. And the title is Experimental Study of Helium-6 Coulomb breakup as an indirect measurement of helium-4 helium-6 reaction rates for the astrophysical process.
Okay. Well, good afternoon. First of all, thanks, Athena, for inviting me to give this talk and give me the opportunity of speaking about, some investigations that we are performing. Well, my name is Àngel Sànchez-Benìtez, and these people, this team, are the main collaborators in this experiment, right? But in the end, I will show the full list of collaborators. Well, the title, Experimental Study of Helium-6 Coulomb breakup as an indirect measurement of helium-4 2N gamma 6 helium reaction rate for astrophysical air process. Well, this is the overview of the talk. So I will present the astrophysical context. Then I will talk about theoretical estimations of reaction rates. Then, which is, let's say, to speak about necessity of doing this experiment, the experiment that we perform in the Nuclear Science Laboratory in the University of Notre Dame. And, in the end, I will speak about, general ideas of the talk. So, okay, astrophysical context, the R process. What is the R process? The rapid addition of neutrons to iron group nuclei that produce the most neutron-rich isotopes up to uranium and beyond, right? Scenarios, astrophysical scenarios, proposed astrophysical scenarios, but proposed not already found scenarios, astrophysical scenarios where these R processes occur in deepest ejecta of supernova and emerging neutron stars, right? Or neutron star mergers, no? Here, I mean, we have this iron peak, and then R process, also S process, but we will speak about the R process, bring us to heavier elements than the iron peak, right? And in here we find a schematic path of the R process, right, which moves through the neutron-rich side, very exotic neutron-rich side nuclei. Well, this in these two slides, first slide, I showed the let's say the publications where they experimentally found a scenario where the R process occur, which is in another double neutron star merger, right? It was published in 2017 and in Nature, and another publication which is linked to the previous one is well, this other publication, which is I mean, everything starts by detecting the gravitational wave event by the LIGO collaboration, right? And then they follow the light curves and then study the light curves, and well, they found that the electromagnetic curves of the observed neutron star merger, NSM, is consistent with nucleosynthesis of A from 80 up to, well, 230. Here we show, I mean, an illustration about the electron fraction of the ejecta, produced ejecta, right? And we can see that we have for electron fraction greater than 0.25, we find the light elements, and then for ejecta below, with the electron fraction below 0.25, we find the medium mass and heavy mass air process element here, right? Here we find let's say different scenarios in terms of electronic fraction that reproduce this side. I mean, from 80 up to 230 nuclei, right? So we can reproduce it using different electron fraction, and well, we can see, for instance, that okay, we reproduce these heavy elements with electron fraction 0.1, which is this side. No? Good. Well, the main parameter for this R process is the neutron to seed ratio. Seeds are heavy nuclei, well, medium mass nuclei in the beginning of the R process, right? So then R process is triggered starting from the seeds in a high neutron density environment, well, 10 to 18, 10 to 20 neutrons per centimeter, cubic centimeter, and high temperature. I mean, from 1 to 10 gigakelvin, right? So then, the main parameter, the neutron to seed ratio, right? That means, okay, but in a neutron star merger, what we have are protons and neutrons, right? So the point is how to reach the starting point of the R process. I mean, the 60 A equals 60 region of the shard of nuclei, starting from alphas and protons. Sorry, alphas and neutrons, right? Not protons and neutrons, but alphas and neutrons, right? So we have to overcome this gap of 5 and 8, right? So how to reach from this part to this part? So the question is how to overcome this gap, right? A, 5, and 8. So this is the path for synthesizing the carbon-12. I mean, because the carbon-12 is the starting point of producing the seeds, right? So how to reach from alpha particles and neutrons to the carbon-12, right? Because once we have the carbon-12, then the path of going to A equals 60 nuclei is understood, right? So then how to reach carbon-12, right? So we have, this is the low mass region of the charts of nuclei. And, well, we can reach the carbon-12 via 3 paths, right? And all of them involves a 3-body nuclear reaction, right? We can get, of course, carbon-12 via triple alpha reaction. We can overcome the A5 gap via this reaction, alpha N producing helium-6. And then once we produce helium-6, then we go through this reaction and produce carbon-12, or we may produce beryllium-9, right, via alpha-alpha N reaction. Three body reactions. In a very neutron rich, which is the neutron star mergers, the latest, these the last two reactions may be competitive compared to the triple alpha reaction producing carbon-12, right? So this is the one path in yellow. We have in red the other path. And then these competing paths, well, these competing three-body reactions, well, so what is more important? We can say that, well, it may depend in the electron fraction, right? So we have here a study publication, this in 2010, that they develop a diagram where in different electron fraction conditions, well, if we think about alphas and neutrons, then the electron fraction, the alpha fraction is expressed in terms of electron fraction, and the N fraction is expressed in terms of electron fraction as well. And then we can expand the whole region of conditions. I mean, the conditions of the electron fraction against the temperature. So we can, let's say, study well, a wide range of conditions where the neutron star mergers are produced. So in these lines, a continued line means that the probability of formation of helium-6 is equal to the probability of formation of beryllium-9. And the gray side, well, is dominant the formation of helium-6. Then in this region, well, we can say the same, but for the beryllium-9. And then, well, region for carbon-12 is here, and we cannot see it, right? But, well, you see that in principle, the dominance of helium-6 may be relevant, right, in these conditions. So now that we spoke about the astrophysical context, we move to theory estimates. So how to estimate the reaction rate of this triple alpha three-body reaction, which is alpha particle plus 2 neutrons. We have for the theoretical predictions, we have a large discrepancies, as we can see here, right? This courtesy from Jesus Casal. But derived from experimental V1 distribution, what we have are large uncertainties, right? Especially in the region of low temperatures. So for that, we spoke experimentalists. I am an experimentalist. I spoke with a theoretical group that, they propose and let's say a framework to evaluate this three-body reaction, the reaction rate of this three-body reaction in an easy way, and feasible, measurable way, so to say, right? So the reaction rate of this three-body reaction can be expressed in these terms. Don't ask me why, but it's like this. And, well, then if we move to the equivalent photon model, we have the reduced breakup probability, which is linked to the breakup probability of helium-6, right? Of course, I mean, in this case. So we have this reaction rate and the reduced breakup probability, right? So these two magnitudes are strongly correlated when we have the parameter, this T parameter equals to 1 divided by Boltzmann constant times the temperature of the environment, right? So if we measure the reduced breakup probability, we can get the reaction rate at different temperatures. So what we should do is to explore astrophysical temperature by measuring Coulomb breakup at energies around or below the barrier and forward angles. Why? Because the conditions of validity of EPM model is that we should have pure Coulomb breakup, right? No nuclear effects. So we will study this reaction, which, how we can produce a strong Coulomb field against helium-6. Okay, we will use a heavy target as the 2A lead, right? And we will study collisions of helium-6 against lead. So, by the way, they produce, when they apply this model in this paper, right? So they use two sets of experimental data of helium-6, but the point is that these two experimental data were measured in an angular region where the Coulomb, pure Coulomb interaction is not warranted, right? So some nuclear interference is expected, as they claim here, right? But they could infer this reaction rate for this three-body reaction forming helium-6, right? But they say here, okay, we should measure at the lower angles and lower energy, and that was what we did, no? Here, I link the, experimentally quantities, like, detected helium-4 and detected helium-4 and helium-6. So we get this in every detector, and then we get the reduced breakup probability via these equations, right? These are the two sets of data that they speak here about, right? These two sets of data were taken in experience that some of us that we are here, I mean, we participate in this experiment made in Louvain-la-Neuve in Belgium, right? We have here the spectrum at forward angles, and we have this bump, and in here we have this detection system, and we could see the helium-6 and then a lot of helium-6, so probably we were getting some scattering in other places than the lead target. So, okay, it deserves a new experiment, so we propose this experiment to be performed in the nuclear science laboratory. So that was and this, you find here the references. And, how was the helium-6 production? Well, using lithium-7 at this energy, so this helium-6 were produced, but, we have also helium-3 at this energy, and then a side reaction, we have helium-4 at this energy, and helium-5, which decays in this helium-4 plus neutron. So this is out of the range, energy range of measurement, right? But also we have a breakup in tantalum windows of the gas cell used to confine the deuterium, right? So we have also alpha helium-4 at 60 MeV, but with a quite different kinetics. So this we didn't find. So measure final energy of the helium beam is 19.3 MeV, and the average intensity below 10 to 4 particles per second. No? This here we find particle identification of the beam using a monitor telescope placed in the target position, right? So we can see here lithium-7, we can see helium-6, and well, if we may make a zoom here, we also see the helium-3, right? So what about the alpha particles? Well, they are out of range, but frame scattering will make them visible as here. This is a picture of the target ladder. So we have here the PIP detector. We have a blank frame of empty frame, right? That in the end was very useful, and 2 LED targets, right? We use this number 6 target, right? Well, some words about the target. They were made in Lisbon and with the collaborators that are part of the experimental collaboration. And they were made in Lisbon and analyzed also in Lisbon in this facility C2TN, which I mean run by Luis Alves and Victoria Corregidor. So we did RBS analysis of the LED target that we use. And we found this thickness, right? And this is a simulation just to study the chemical composition of the target. So, I mean, the purity is rather high, and lead 208, right? So we spoke about the beam, about the target, the detectors. Here you have the detectors. And here it is this is the lab angle against the laboratory energy, right? Kinetic energy of the beam. So our region that we are measuring is here, right? 19.3 MeV, and this angular region, right? The detectors were from the laboratory, right? And okay, the ongoing analysis. When we get this is cumulated data using the LED target, so we find here a lot of alphas and also helium-6 frame scattering helium-6, right? These are all the strips cumulated, right? But when we put the blank frame up, sorry, that was spoiling. When we put the blank frame, we can see also the alphas and some helium-6. So this we must subtract if we want to pick up the alphas coming from the Coulomb breakup. These are measurements with the LED target or blank target, right? Because we always use the blank target, the empty target, so that we can subtract the contribution of the frame. Sorry, and this is this is with the LED target. This is with the cut in the alphas, and we do see this distribution, right? And well, when we go to this strip by strip, right, we can see the evolution of this bump, which is the bump that we can the bump that is made of these alphas coming from Coulomb breakup. So this is a summary of my talk. Well, essentially that we have a framework, theoretical framework that may help to get indirect experimental measurement of the 3-body reaction rate. And okay, this take care of this. The data analysis made so far shows the importance of carefully study the frame scattering beam induced background, right? This is the collaboration that well, so far of this experiment, and thank you for your attention. Nice to see you, Agatino.
Okay, you stressed, and I agree with you, having this problem of A equal 8 gap that in some way must be solved. Can you comment on some other channel that can be available specifically in explosive scenario like I don't know, Big Bang nucleosynthesis, something like that?
Well, really, this the R process that you see. I'm speaking about R process, right?
Yeah.
An R process. I'm as an experimentalist, nuclear physics experimentalist. I'm happy that they detect a scenario where R process is occurring, which is the neutron star mergers, right?
Yeah.
Other scenarios.
Yeah.
Well, personally, it is a question whether the R process can make up all the elements that we can found. I mean, if it is the occurrence of R process in these neutron star mergers and this and that is too little. So some people claims that it may be something well, not the R process but S process may start a lot in advance in the story of the universe, right? But this is an open point, right? So I don't know if
I don't know specifically for the lithium 8 alpha and in
this lithium 8 alpha. I mean, if it is important in this context, the lithium 8 alpha, as far as I know, is not competitive.
Okay.
I mean, because there are some theoretical works pointing to these three-body reactions, right, or three paths. But the lithium 8, okay, is an alpha-rich environment. So, but I didn't find anything about lithium 8 alpha.
Okay.
Next
Thanks.
question, please.
Ángel, when I read the paper of Calampo et al., he mentioned that this alternative method is a robust method. So my question is, the precision of this measurement, will it be better than before or not? Because I understand the robust is that you have an interference perhaps between nuclear and Coulomb, or you have an interference between E1 and E2 polarities.
For this particular situation, that experimental conditions that we had in Notre Dame, I didn't bring let's say the estimations, right? But I did some similar estimations for different telescopes and slightly different energy of helium-6 beam, and very easily in this case we can get uncertainties much lower than the uncertainty we have right now with this experimental data from Tom Aumann
But
and
I don't
GSI.
mean for statistical uncertainties, okay? I mean for the uncertainty in the theory itself.
Well,
when you try to calculate the reduced probability.
we have two scenarios there. No? First, if we guarantee conditions for pure Coulomb breakup, that means very straightforward, very forward angles, right, and energies below the Coulomb barrier, then in principle, this is not an uncertainty in the model because we have pure Coulomb breakup, right? Then the second point is that if we have some nuclear interference, they claim that they can subtract this contribution of nuclear interaction to the calculation, right? And we have a third point, which is that we can compare what we have experimentally with what we have, the breakup probability that we have with the breakup probability that they can calculate with the EPM model, right? So if it fits, right, then we can consider that we are in the conditions where the EPM model works. And then there is no approximation. Higher order contributions electromagnetic interference are not relevant at all. They claim.
Well, okay.
We can continue in voting.
Yeah, we can continue, yes.
Yes, please. Okay, thanks again. The next speaker is Theodoros Depastas from Texas University, and the title of his talk is An Imaginary Time Study of Carbon Band Stellar Emissions.
Hello again. My name is Theodoros, and in this talk I will talk about the work we did with my advisor, Dr. Aldo Bonasera, regarding the imaginary time study of the carbon and helium burning processes in stellar conditions. First of all, I'll give a brief introduction to the semi-classical models that we're using, that is the HAC and the NEC model. As we know, the alpha particle is one of the most stable nuclei in nature, and for that reason can appear as a cluster in a heavier nuclei. For example, carbon-12 may be considered as a set of 3 alpha clusters. This specifically is the basis of the hybrid alpha cluster model, or HAC, that considers the alpha particles as fundamental degrees of freedom, which evolve through semi-classical equations of motion via the Hamiltonian interaction containing a kinetic term, an effective Fermi energy term that actually corresponds to the Pauli repulsions of the inner constituents of the alpha particles in cases of overlap, a nuclear bus potential, and a Coulomb potential. This model has already been used both for fission and ground state studies successfully. Next, we're moving towards the NEC model, which we actually described a little bit in the morning talk. So essentially, the NEC model is the classical limit of the time-dependent Hartree-Fock under its Wigner representation, and it considers that during either fusion or fission, the total nuclear volume is conserved, so a NEC is formed with radius Rn here, and another distance between the center of masses. And these are actually the 2 degrees of freedom that evolve according to a semi-classical equation of motion, with the bus potential, which we have modified in order to create the resonance of the compound nucleus, as well as a nucleon exchange through the NEC. This has also been studied for fission and fusion, as we have discussed in the previous talk. We'll now move towards the imaginary time method, which is actually the tool that allows us to study a quantum effect, such as tunneling, with the semi-classical model. Initially, the 2 nuclei are moving towards one another, and at some point, they stop when they have low energy due to the Coulomb repulsion. At that exact point, the classical turning point, the time changes from real time to an imaginary time I tau, which essentially means that due to the quadratic dependence of the forces, we get an extra minus sign. So the forces invert sign. So for example, Coulomb that is repulsive in real time, in imaginary time becomes attractive. So the nuclei are moving again towards one another, and at some point they stop. Why they stop? Because the nuclear part becomes important, which in real time is attractive, so now becomes repulsive. The nuclei exit the imaginary time, return to real time, and then they fuse. Schematically, we can see this for a Vlasov calculation here. So we have the 2 turning points. Here we have the collective momentum and the relative distance. And actually, the integration of the area gives us a classical action, which is inversely dependent. It's depending inversely on the tunneling probability. So high action, low tunneling probability, as we give by this formula. With these 2 tools, a semi-classical model, either the HAC or the NEC model, and the imaginary time method, we're able to study sub-barrier resonant reactions. So let's start with carbon burning that was also discussed in the previous talk for the Trojan Horse Method. We have 2 carbon nuclei, fusion, creating a magnesium compound nucleus, which can then decay. Now, this is a quite complicated plot, which we'll break down. It shows the astrophysical factors, which is actually the nuclear component to the cross-section as a function of the center of mass energy. First of all, we have the HAC results, which are given by the red curve. And we see that they are a smooth function of energy from 10 to the 15th around to 10 to the 17th MeV barn. Next, we see that the high energy part more or less describes the available experimental data sets and the Vlasov calculations represented by this triangle, as well as the NEC model results that have already been studied. Moving on towards the gamma window, which is the energy that actually have the ions inside the star, the experimental available data are given by the Trojan Horse Method, as was described previously. We see that there are several resonances appear, but also the baseline is increasing. And it's actually some orders of magnitude greater than the HAC model. The HAC model, of course, does not represent the resonances due to its semi-classical nature, but even the baselines are quite different. For that reason, we tried a new approach that is to study the fusion of a carbon in its ground state with a carbon in its first excited 2+ state. And we see that this describes, apart from the resonance structure, the Trojan horse data on an adequate level. That is quite important because might suggest possible mixtures of the 2+ state in the Trojan horse remnant. Of course, that is not sure. So for that reason, we need more studies towards that direction with the Trojan horse method. The next thing we do is that we correlate the oscillations of the astrophysical factor represented here with collective motion. So in this graph here, we have the astrophysical factor with the HAC model divided by the corresponding values given by an analytical formula that we have constructed. This essentially takes out all the mean field dynamics and leaves us only with collective motion. So this essentially corresponds to the collective spectrum as a function of excitation energy. The blue line corresponds for the L = 0 collective spectrum. And we see that at least in the low energy region, and apart from this cap K0 peak here, the monopole spectrum for the magnesium-24 is obtained. The monopole, of course, is a giant resonance that describes the breathing mode of the nucleus. The red line now corresponds to L = 2, a quadrupole motion. And we see that the experimental maximum is given almost exactly on top of our peak. Of course, the quadrupole, I should point out here, that corresponds to the oblate-prolate shape oscillation of the nucleus. So using these tools, we can also extend our study to the helium burning process. The helium burning process, also known as the triple alpha reaction, corresponds to 3 alpha particles moving towards one another, fusing and creating a carbon-12 nucleus that can decay via 2 gamma photons with a branching ratio close to 3%. So we consider this as a 2-step approach, and we have actually constructed a novel theoretical framework to cover the entire thing that we actually compare with one of the most famous theoretical frameworks, that of the NACRE collaboration. So we use a complete compound nucleus method. So the fusion for the cross-section for the second step is given by the fusion cross-section over the branching ratio that is given by the ratio of the widths. On the other hand, NACRE formalism uses a Bright-Wigner approach that is approximately equal to the division of the gamma width over the alpha width. As for the widths, the NACRE collaboration uses a constant proportionality factor between the tunneling probability and the alpha width, while on the other hand, we correlate the tunneling time, that is the time between the ions, to the width. We also consider that the resonance structure of the alpha width is proportional to the gamma width, so we add a resonance correction to the usual parameterization. Our resonance cross-sections can be shown here for the second step as a function of energy. I will move a little bit quicker. We see that the HAC data are more or less equivalent with the NEC model data apart from the resonance, and that the cross-section is more or less independent of the excitation energy of the beryllium-8 nucleus. This can be used to calculate the reaction rates. The reaction rates are given by this integration of over the energies of the 2 alpha particles in the first step, creating the beryllium, which we start from the 92 keV threshold instead of the 0 that is start from the NACRE collaboration. This actually has very serious consequences because in the low energy region, we see a 20 to 30 order of magnitude enhanced cross-section when the integration starts from 0. So in order to constrain this, we searched for several criteria. And these criteria are given astrophysically by Suda. So in order to have observed luminosities, the purple point gives the maximum reaction rate. All of the cross-sections follow under that line. The green one is the NACRE, the blue one is the NEC model, and the red one is the NEC model, the HAC model. Another constraint is the lower limit in order for the star to experience helium flashes for the derivative with respect to temperature, and again, all the cross-sections are above that limit. What this tells us? This tells us that we need more stringent constraints, most probably given by nuclear physics, and perhaps again with the Trojan Horse method because it has the option perhaps to bypass the short lifetime of beryllium-8 nucleus. At this point, I would like to conclude this short talk. We have studied using semi-classical models coupled with the imaginary time method, the carbon and helium burning steps. We calculated cross-sections, we calculated astrophysical factors, and we actually correlated the astrophysical factors with subbarrier resonant dynamics. We constructed a novel theoretical framework for the triple alpha reaction, and is consistent with the current astrophysical and nuclear data. At this point, I would like to thank the organizing committee for accepting the talk, and all of you for your attention.
Question, please. Any question, please?
Thank you for this nice talk. For me, just to understand. Thank you. For me, just to understand, I don't get the notion of this imaginary time and the transition from the original time, normal time, to imaginary, then back to this one. It looks like a region to me, but what is the meaning of this imaginary time? It's like a term or just really time?
So this is actually a question that has pondered several scientists, such as Stephen Hawking or Feynman when he used for the path integrals. To my understanding, imaginary time is normal time under the Coulomb barrier. So we need to represent the tunneling somehow differently using semi-classical models. This is a quantum effect. We cannot do that. So we include this mathematical trick when they stop. So the time gets an extra I. The forces are second derivative of time, I square minus, the forces change. They continue moving below the barrier, they change it again, they stop, and then they move to real time.
So just a line, it's a timeline, but just changing the imaginary to normal time.
What is imaginary?
In terms of mathematics. Yeah, thank you.
Welcome.
Sorry for my ignorance. So I would like to understand, there are physical features of this kind of approach with respect to the classical tunnel theory. So there are, specific features that can associate, this description, to some experimental. Yeah, no, the classical tunnel theory we know very well, okay? But I try to understand if this approach, imaginary time, is going to give us additional feature or additional, revision about the process.
So in order for the classical tunneling to happen, we need the momentum to be real. And for that to be real, the square root of energy minus V should be positive, but below the barrier is negative, because V is greater than E. So this thing here tells us that the momentum gets the imaginary part. This actually enables us to study, to use these methods with microscopical models. The hybrid, the
point of view of the experimental evidence.
The experimental evidence of tunneling. Or
with respect to the tunneling, if you compare tunneling and your approach.
This approach is tunneling. Apologies, I don't understand exactly the question. The experimental data are represented here, and the approach can calculate cross-sections, which we then compare to the experiment, if that's what you mean.
But you get the same result by using the normal tunneling theory.
The normal tunneling theory with a quantum model, yes, but has other problems because it's a mean field model. So we cannot observe non-mean field dynamics. We cannot observe correlations, collisions. So we need to solve this problem with a molecular dynamics code that has all these nice features, but that also poses a constraint on how we do the tunneling. I hope I covered your question. Well, means.
Time for this not clear. Is the times the real time, or is like something, some parameter or something like this? For me, it's not clear.
Yes, actually, I have some extra plots. Let me give me a moment, please. Which I think will clear the things out. So here we see the total energy as a function of time for a specific event, for a specific center of mass energy. During the barrier tunneling, the imaginary time, because the forces change, there is some extra work. But this is covered with the Heisenberg principle, delta epsilon, delta tau, h bar. So we connect this tunneling time with the width. The width is inversely proportional to the tunneling time, as we describe in this here. So that is essentially the tunneling time, which is the time below the barrier, and this real time, normal time, is corresponding to the width. So larger time below the barrier, larger imaginary time, higher, smaller the width, more narrow the resonance. If I, of course.
I have a question regarding the semi-classical approach, because at this low energy, the wavelength of the relative motion could be not so small. I mean, yeah? And the semi-classical approximation requires that the wavelength, so the wave pockets, are very small compared to the nuclear radius. No? I have the impression that, especially when the two nuclei almost stops, the wavelength is so large that semi-classical approximation cannot be used at all.
So essentially here we invoke the Ehrenfest theorem. Semi-classical approximation between a delta potential, that this Kerm-like potential is the most useful one, and Gaussian wave functions, it's exactly the same as delta wave functions, which essentially is classical mechanics, with the Gaussian potential. Essentially, these are almost equivalent descriptions as was described first by George Bertz and Dr. Bonacera in the Phys reports. So for that approximation here, we of course include a semi-quantization with, give me a second please, this term. This term includes some quantum phenomena ad hoc. When the two interact, they should be repulsed due to the constraint of the phase space of the Pauli and Heisenberg principles. So that is somehow, yeah, of course, I'm not saying that we have full quantization. I mean, this is still an open problem from Einstein's time to deal today. But that corresponds to both the experiment and our current theoretical understanding with equivalent methods like the Vlasov, for example, which in a sense is almost has some classical equation of motion for fluid type situations.
But that's typically used at intermediate energies, not at so low energy. That's the question.
Well, to be honest, we see in the literature that Vlasov can go even to lower energies. I mean, in this plot there are several data sets that do that, and more or less they present the results. So this is Vlasov. All the way here, this is Vlasov, this is NEC model, and they're very close to experimental data. You pose a very valid question, which I would like to be, thought a bit more, but essentially from Ehrenfest theorem, we can use that as a trick of the evolution of the expected values.
Okay, you can continue to report.
Thank you.
This is phase transition.
We continue with Isovector properties of finite nuclei and relations to neutron stars.
Okay, thanks. The title of, first of all, I would like to thank the local organized committee, and especially Professor Athena Pakou. I think she's not here, but it's okay. The title of my talk is Isovector properties of finite nuclei, constraints from the neutron star observation. This is a part of my PhD students, Manolis Divaris, and I will try to shortly present some our results. Okay, the structure of my talk is firstly I will talk about the basic formalism of finite nuclei, just introduction, about the neutron skin thickness, the equation of state of neutron star matter, also about the basic formalism of neutron star structure, and the tidal effect, which is very important which is related with the gravitational waves. I will present the results of our research, and finally the conclusions of this talk. Okay, this is the basic formalism of finite nuclei. This is the well-known Bethe-Weizsäcker formula for the binding energy of nuclei. Especially we'll concentrate our study in this part, which is related with the symmetry part in the Bethe-Weizsäcker formula, the difference between the number of neutrons and protons, and special to these coefficients. We know also that we can expand these coefficients, which consist of two parts. The first one is the volume asymmetry coefficients and the surface asymmetry coefficients, which relate with these relations. And now, if we want to calculate, for example, the total energy of the nucleus, this is with the help of the density fractionals. The integration of the energy density give us the total energy of the nucleus. This is the asymmetry parameters, which relate with the difference between the distribution of protons and neutrons. And also, this is the density distribution, the total density distribution inside of the nucleus. And we can define also, with the help of the density fractional theory, the asymmetry coefficients, which given by these relations. Here is also the density distribution. This is the symmetry energy, which is a fractional of the density, and also the asymmetry function. Okay, this is the basic formalism to calculate the few of the back properties of finite nuclei. The neutron skin is the difference between the radius of neutron and protons, which is defined from these relations. And we have, firstly, to say that this thickness is not directly related with the symmetry energy. For example, as you can see here, both proton and neutrons related with the symmetry coefficients, but not of the symmetry energy. But indirectly, we will see below that there is a connection between the skin thickness and the symmetry energy. And also, directly, these coefficients, the symmetry coefficients related directly with the symmetry energy. And we have some final experiments. Of course, there is some kind of contradiction about this value, that the neutron skin thickness is about 0.28 Fermi minus plus 0.7. This is let's say, a little big value of the neutron skin, but in the present work, we consider that this is, let's say, good constraints for the thickness. Okay, about some simple words about the question of states of asymmetric nuclear matter. We can expand the energy per particle around the saturation density. Here is the incompressibility of symmetric nuclear matter, and here is the symmetry energy. We expand also the symmetry energy around the saturation density. This is the basic coefficient of these expansions. The main quantity in this study is the slope parameter, which is related with the stiffness of the equation of states. And also we use the incompressibility related with the symmetric nuclear matter. And we combine these two parameters, and we use this, the new parameter, which is a combination of this value, the compressibility and the slope parameter, in this way. And we have just only one parameter to construct the equation of states. Okay, now we use, let me say that we use this function also to calculate the back properties of finite nuclei. And also, we are going to apply also this formula to calculate the neutron star properties. Of course, the normal question is, okay, in finite nuclei, the density is very low, up to saturation density, but in neutron star, the densities are 5 or 6 times the saturation density. How you use the same functional both from finite nuclei and neutron star. But we try and we see that this functional works nicely also in finite nuclei and in neutron star. maybe the explanation is that this is a very simple expression, and playing with a parameter, it's very easy to reproduce the neutron star properties just playing with the value of the slope parameter and the compressibility, especially the slope parameter. Okay, this is how to construct the equation of states to describe the neutron star properties. Here is the baryon pressure, which is the derivative of the energy density. Takes this form in this our very simple approach. We have to add also the pressure from electrons in the total energy and pressure. And one has to solve this system of differential equation to calculate the back properties of neutron star, that means the mass, the radius, and the density distribution inside of the star, and so on. But the key quantity is here. This is the energy density factor, which used both in finite nuclei and in neutron star. And finally, about the theoretical formalism, this is the tidal effect. Tidal means how easy it is to deform the neutron star. This is that's the basic quantity which is related with how easy to deform a neutron star, because this is not so easy. It's a completely spherical object. But when we have a binary systems, one neutron star close to the other, then the attraction is very strong gravitational field, and we have some kind of deformations. And we are lucky because gravitational waves give a lot of information about the tidal deformability. And since the tidal deformability is related with the radius of the neutron star, we are able to get very good information about the radius of neutron star. Because in the previous years, we have very large uncertainty. Now, with the gravitational waves, we are able to constrain much better the radius of neutron star, and this is very important, especially related, since the radius of neutron star related with the low part of with the low density part of the symmetry energy, that means with the properties of finite nuclei, more or less. Okay, this is what happens. We have a binary systems, and during the spiral, there is they radiate gravitational waves. We get the gravitational wave. We analyze the phase. We analyze the frequency of these waves and the amplitude, and we get information about the basic structure properties of neutron star, mainly about the radius, the tidal and the radius. Sometimes also about the mass, but mainly about the radius and the tidal deformability. Here is some results. You can see here we compare our equation of states. This is the part of our equation of states with some more complicated, more elaborate equation of states. We can see that the trend is also similar. That means even the simplicity, this equation of states works nicely, also both in low and also at high densities, baryon densities. And here is the predictions. Here is some constraints from the NICER, from observation of gravitational waves, which you can see here that depending on the value of the parameter eta, that means for low values of eta means soft equation of state. High values mean stiff equation of states. You can see here that we are able to constrain this value just for observations. This is another very recent event, but this event is, at the moment, we are not able to explain with a classical hadronic equation of states. This is just for comparison. And also here is the tidal deformability. This is some constraints from observations, from gravitational waves. The tidal deformability as a function of the mass. And we can see here our predictions and the constraints. Also, this is average tidal deformability average between the system of two neutron stars, because when we get information about the average value of the tidal, not for a individual neutron star, just for the combination of them. That is the value. This is the, let's say, the average as a value of the symmetry of the mass of two neutron stars. You can see also here that there is some constraints also on this value of eta, and here we relate also the tidal with this value of eta. This is the predictions. You can see here that that means that the observation said us that the more preferable values of eta is less than 100. because you can see here this is the inside of the observations. Also, we relate also here the tidal and also the skin. You can see here that it's not so easy to, at the same time, to produce the neutron skin and also the observation of the gravitational waves, the detection of gravitational waves, that means the tidal. That means a kind of, how can I say, we are be able to reproduce, for example, the tidal, but not at the same time with the same value of the parameter, the neutron skin. And I will explain my results. Also, here we have, for the first time, predictions for the asymmetry parameter, and we relate this value with the tidal. We can see here we have some constraints from observation, and the final result is that the value of neutron skin, the experimental value, is very high. That means we need a large value, we need stiff equation of states. This is the first result. On the other hand, if we compare, if we try to reproduce the observation of the gravitational waves and the prediction of about the tidal deformability, the more preferable value is for soft equation of state. That means for low values of theta. There is a kind of contradictions. This is a problem, of course. We are trying now to see how to improve our calculations in order to be able to see the best constraints for the value of theta and consequently on the both of the neutron skin and also the value of the asymmetry parameter. The conclusion is, as I said before, the neutron skin is very sensitive and also these coefficients on the stiffness or softness of the equation of state, that means of this parameter. The effect is very dramatic, especially for high values of theta. Also, for the neutron skin thickness, in order to be compatible with observation with experiments of PREX2, the values must be around 100 and 125. Also, we found also that there is a effect. There is effect of this value on some of the other back properties of neutron star, for example, of mass and radius, and also by applying the observational value limit of this tidal, which corresponds to 1.4 solar masses in neutron star, we found that there is an upper value of this value is around 106, and that means that all these equation of states reproduce the observations. This is the upper limit from this value. Okay, and the main results, okay, I don't want to analyze all these results. The main results is that we use in this work just a very simple model with only one parameter in order to relate the finite nuclei, which is a distance around just few Fermi, with a neutron star, which let's say an object around 10 kilometers or more. And this is, we try to do it just using a simple equation of states with only one parameter. And we try to see how easy it is to impose some constraints on this value of this parameter. Of course, the other way is to use a very large number of equation of states to calculate, firstly, the back properties of neutron star, and secondly, to use a very large number of equation of states to calculate the properties of finite nuclei and try to see to correlate using some kind of machine learning or this kind of data analysis to relate these properties. But in this model, what we did is just using a simple model describing at the same time both finite nuclei and neutron star to see some kind of correlations. Okay, thanks for your attention.
Thank you for the nice talk. Are there any questions, comments? Give some time.
You mean about? Just to see. Yeah, it means this is this event.
The other one.
This one.
The radius, mass radius relation.
Here is the mass radius relation. Here is.
This band at around 10 kilometers.
Ah, this is the new event. No.
But this is really so small.
No, this is a new event. Maybe later one of my PhD students will discuss about this problem. This is a new event found around 3 years before. This is a neutron star with a very low mass, around 0.7 solar masses and around 10 kilometer radius. We are not be able to explain with a usual hadronic equation of states. That means it's very hard to say this is a neutron star and the equation of states would describe this object is a equation of state of neutron star equation of states. That means maybe something different. Maybe this is quark star or this is a hybrid star. Or we don't know what is this. But just I plotted here to show you that at the moment we are not be able to explain this event with the usual standard neutron star equation of states. This is an open problem.
Thank you. So if there are no other questions, then we can proceed. Yeah, thank you, the speaker.
Okay, thanks.
Now we have some small changes here. Konstantinos Folias will be the next speaker. And will tell us something about quarkyonic patterns, again in relation to neutron stars.
Άνοιξε το λίγο. Κλείσε από εκεί, κλείσε από εκεί, κλείσε. Άνοιξε το, ναι. Άνοιξες εδώ πέρα κάτω, εδώ, σε εκείνο, λίγο πιο πάνω, δεξιά, λίγο πιο πάνω, πιο πάνω. Αυτό είναι χτύπωτο. Και κάτω, κάτω πολύ full screen.
Hello everyone. My name is Konstantinos Folias. I'm a PhD candidate in the Department of Theoretical Physics in the Aristotle University of Thessaloniki. And today I will talk about my PhD thesis. I deal with quarkyonic matter and applications in neutron stars. In this presentation, we will see the following. First of all, an introduction to quarkyonic state of matter. What is this state of matter? And what is the motivation which lead us to introduce this state of matter? After that, I will present my model, a model that consists only of neutrons, down and up quarks. We called it NDU quarkyonic model, and neutrons interacting via momentum-dependent potential. After that, we constructed the equations of state, and we compute sound velocity for the models. Then we apply these equations of state in cold neutron star. We solve Tove equations, Tolman-Oppenheimer-Volkov equations, and we construct some diagrams, mass radius diagrams. Finally, we'll discuss our results, and I will mention some open questions of this theory and some perspectives. Let's start. What is this state of matter? We consider that this state of matter occur at large densities and Fermi energies. And what is this? We assume that quarks occupy low momentum states in the phase space up to a Fermi momentum, and baryons form a Fermi cell at higher momentum states with a width about delta. This description can be illustrated in the following picture. This is the phase space where quarks form a Fermi sea in the phase space, and baryons occupy higher momentum states. These are the distribution functions. Now, in this model, we assume that chiral symmetry remains broken, so the quark mass is obtained by this relation as the mass which have a quark inside the nucleon. And C is the number of colors. For Fermi momentums, we assume these relations. This becomes from the basic assumption of the theory that the greater momentum state of quark, the Fermi momentum of quark, is equal to the lower momentum state of a nucleon. And these relations becomes from the charge neutrality. For the thickness of the cell, for the width of the cell in the phase space, we assume this relation, this phenomenological relation, where lambda, the parameter lambda, is about the QCD scale, and the kappa parameter is about 0.2 to 0.3. Now we compute the baryon density, the number density of quark. We can see that we integrate over the momentum space up to a Fermi momentum, and we start from the momentum 0. There is the Fermi sea in the momentum space, and nucleons reside in the Fermi cell with a width which is the delta. After that, we compute the indirect density. First, for quarks, we sum over the up and down quark. And for the nucleons, in the general case, we have neutrons and protons. We'll see in the model how it will change. Initially, we consider that quarks are non-interacting, and only nucleons interact via potential. Finally, we compute the chemical potentials for each piece of matter and the total pressure to construct the equation of state. Now, our model is the so-called NDU quarkyonic model. It consists only of neutrons, up and down quarks. And quarks interact via momentum-dependent interaction. This is the interaction. This is the potential energy. It consists of 3 terms. U is this fraction, and 0 is the saturation density. Now, each term is the first one. The first 2 terms are momentum independent. The first corresponds to an attractive interaction, this term. The second one corresponds to a repulsive interaction, and it's dominant for high values of the density. The third one is the momentum-dependent part, and corresponds to an attractive interaction, and has been introduced to include the finite range forces. So in our model, the total energy density is in this form. The first term is for neutrons, and the second 2 terms is for up and down quarks, respectively. The parameters of the potential is in this form. We set up the number of colors to be equal to 3, and the degeneracy of the spin to be equal to 2. Now we construct the equations of state for several values for the parameters lambda, and for several values for the transition densities. Transition density is the density where we insert the quarkyonic matter. Below this density, we assume that we have only neutrons. We have a pure hadronic matter. We calculate the total pressure, the energy density, and finally the sound velocity to to see if our equation of state are causal or not. Now, we construct several equations of state. We can see, we can see with the red line a pure neutron model, and with the different colors, we have several values for the transition density from 0.2 Fermi to the power -3 up to the 0.4, the blue, the yellow, green and black lines respectively. And the different shapes of the curves corresponds to several values of the parameter lambda. We set up the lambda to be to have these three values, and we see the solid line for the 160 MeV, the dotted and the dashed dotted lines with 180 and 200 MeV respectively. After that, δεν ξέρω τι πάτησα. Να το κλείσω. Δεν ξέρω τι έκανα. Α, εντάξει. Νομίζω... Α, okay, okay. After the construction of equations of state, we apply them in Tolman-Oppenheimer-Volkov equations to calculate mass, pressure, and radius for a neutron star. TOV equations are in the following form, where P is the total pressure, M is the mass of the star, rho is the mass density and the gravitational field. And we construct the MR diagrams, mass versus the radius. Here we can see some recent observational data. The purple contour plot is from LIGO observations, and this is from the HESS experiment. The different colors correspond, as before, to different values of the transition density, and the different shapes for the several values of the lambda parameter. We can see that for transition density about 0.25 Fermi to the -3, our predictions are inside the observational data, but we have to ignore transition density for the value of 0.2 Fermi to -3. Okay, and then we calculate tidal deformability and we construct these diagrams. This is the logarithm of tidal deformability with respect to the mass of a neutron star and respectively as a function of the radius of the star, as before. Finally, we have to note some interesting feature of this work. First of all, we have to note that quarkyonic matter can provide the speed of sound as a non-monotonic function of the baryon density. We have a rapid increase of the sound speed up to a maximum value. After it decreases, and eventually it is reaching the conformal limit. Also, quarkyonic matter can provide massive neutron stars, about 2.5 up to 3.5 solar masses, without violating the causality. And this is the main reason we insert this theory. and it predicts a little greater radii compared to pure hadronic models. Also, we constrained some macroscopic values of our models. The lambda from causality cannot be greater than 210 MeV, and from LIGO and HESS experiments, we have that we have the extra constraint that the transition density can't be greater than can't be lower than 0.25 Fermi to -3. And this state of matter may be a consistent way to explain the phase transition inside a neutron star. Also, we have to note some interesting perspectives and some open questions of this theory. First of all, is there any fundamental theory which can provide this state of matter with a consistent way? Also, can we apply this theory in finite temperature neutron star? Our results will change if we insert protons and electrons to impose beta equilibrium. Can we insert strange matter in this theory? Do we have chiral symmetry restoration after the phase transition, or it remains broken? And can we constrain further the microscopic parameters of our model from new observations from gravitational waves? Finally, I would like to thank my supervisor, Professor Charalampos Moustakidis, for his guidance throughout this work, and all of you for your attention. Thank you.
Thank you very much. It was a very nice time. Are there any questions, comments?
Yes. Okay, very nice talk. Thank you. My question is very simple. This quarkyonic model, the up and down quarks are, I assume they are at the confined phase. Where you find them free?
Yeah, we
said here symmetry.
We assume that are
is
free.
broken. Yeah.
That for high densities we have asymptotical freedom.
Yeah. So you assume this model that the quarks are the bare phase, so it means that they're just, let's say, deconfined.
It's not a pure quark phase, it is an hybrid state of matter.
Okay.
We assume that for low momentums, the degrees of freedom are quarks, and for higher momentum states, we assume that particles are confined into nucleons. It is phenomenology till now. There isn't a fundamental theory to explain this state of matter. Till now. In the future, it is an open question.
Okay. Thank you. Thank you.
Maybe one question? No? Okay, then thank you very much again.
Thank you.
Next speaker, Pavlos Laskos-Patkos, which will tell us something about hybrid stars and the stiffness of the question.
Presentation.
So hello to everyone. I'm Pavlos Laskos-Patkos. I'm a PhD student at Aristotle University of Thessaloniki, and today I'm going to present you our recent work on hybrid stars in light of the PRX2 experiment and this long expression about the HESS J1731-347 remnant. From now on, I'm going to call it HESS for simplicity. Part of the results that I'm going to present in this talk can also be found in our related publication, which is shown below on the screen. So as an overview of the talk, we are going to talk about neutron stars and neutron stars observations, although this we are going to talk about briefly as it was covered in previous talks. Then we are going to talk about the supernova remnant at hand, the PRX-2 experiment and how does it relate to the stiffness of the nuclear equation of state, what is the purpose of the study, the mathematical framework briefly, and then we are going to present the results and their implications. So neutron stars are considered to be unique extraterrestrial laboratories for the study of dense nuclear matter, and this is somewhat expected considering the extreme values of their properties. So we have extremely large densities, extremely large magnetic fields, masses, and very small radii. And as you can see in the right-hand side of the picture, even though the layers of the neutron star are kind of well known around about the nuclear saturation density, there is a large question mark in the middle, because at that part of the star we do not know the degrees of freedom that are the relevant and the dominant ones, and also we don't know how they interact. So the key question is that, can we somehow leverage neutron star observations in order to gain some information about this particular place of the neutron star interior? So in principle, the way that we are going to do this is that different nuclear models predict different equations of state, which in turn predict different neutron star bulk properties. And hence we can use observations and measurements on neutron stars to constrain nuclear models. For instance, in the past decades, the observation of massive neutron stars above 2 solar masses has posed a significant challenge. So an abundance of nuclear models and equation of state have been rolled out. And very recently, just like 5 or 7 years ago, we have the first radius measurements that were accurate from the NICER mission, and also we have the gravitational wave data, which provide additional constraints at around intermediate densities. So let's talk about the supernova remnant at hand, and why do we care about it? So around the late 2022, a surprising observation came. So by analyzing the X-ray spectrum from the central compact object in the HESS remnant, Doroshenko et al. Found very surprisingly small values for its mass and radius. So they have found a subsolar mass neutron star that has a radius around 10 kilometers. This does not sound surprising, but actually from an astrophysical perspective, the mechanics, supernova simulations are unable at the moment to end up with a stable configuration with such a low mass. And also this radius is kind of low if we consider other nuclear experiments. So, and why do we care about it as a second reason? Is that up to this moment, the low density part of the nuclear equation of state was mainly constrained via Earth-based experiments. And this low mass neutron star with a low central density allows us to have an additional way of constraining the properties of nuclear equation of state around nuclear saturation. In particular, the radius of subsolar masses neutron star correlates very strongly with the slope parameter and the incompressibility of nuclear matter. So it relates to the symmetry energy, and also it relates to the curvature of symmetric nuclear matter. So the radius of such a small neutron star can be directly related to the symmetry energy properties. So let us now talk about the PRX-2 experiment. Actually, this experiment was running about in 2 stages for about 20 years, and it provided in 2021 a value for the neutron skin thickness of lead, which was surprisingly large. And this is interesting because this property correlates to the symmetry slope as well. From the previous observation, we had that the radius is small, and therefore the slope parameter needs to be small as well. But now we have a large neutron skin thickness, which correlates to a large symmetry energy slope. It is honest to comment that there is some debate on the validity of the PRX-2 results, because the same group has published the results for the neutron skin thickness of calcium, and these 2 results are in tension, actually. But it's rather interesting to see this specific experiment in this study, and I'll explain why. So, as you can see here, from different analysis, you can see the blue shaded region, which is what should be the radius of subsolar masses neutron star if the PRX-2 results are valid. And this is very far away from the 10 kilometers predicted by the HESS observation. So the main question is that how could we use nuclear models that fit the PRX2 results, but also can explain such a low radius neutron star observation? And what we're going to apply is a possible phase transition to a phase of deconfined quark matter. So in the question mark in the center of the neutron star, we are going to assume that the degrees of freedom are mainly U, D, and S quarks. And in order to do that, we are going to construct hybrid equations of state. For the hadronic part, we are going to use 3 different Skyrim effective interactions which scan the range of the neutron skin thickness predicted by the PRX2 experiment. And for the quark equation of state, we're going to use one of the most widely employed phenomenological parameterization, which is the VMIT back model, which actually has a term that is related to the Fermi energy of quarks, a term that is related to a repulsive interaction that is mediated by a vector boson, and the so-called back term, which is an attractive channel. And we're going to do this thermodynamically consistently via the Maxwell method, which is described by the last 3 equations. And finally, we are going to investigate 2 different scenarios with regards to the back parameter, the parameter B. In the first case, we are going to assume that it is constant, as in standard MIT back models. And in the second case, we are going to apply a simple density dependence, which is the most widely employed one in literature. And it is the Gaussian one. So let us start with the results. As you can see, for the case of constant bag, with the black lines, you can see the MR diagrams predicted by the stiff equations of state that are compatible with the PRX2 experiment. And with red, you can see the equations of state with phase transitions, which also pass through the confidence interval for the HESS observation. The gray ones are phase transition equations of state with phase transitions that do not satisfy the constraints. And as we can see, a strong phase transition is capable of reproducing both events simultaneously. However, there is a problem that one cannot see in this figure, and this is other astrophysical constraints. If we plot the maximum mass predicted by each equation of state as a function of the transition density, we see that the conservative 2 solar masses constraint places very strong constraints on the transition density, and it places it close to the nuclear saturation density, which we know that the dominant degrees of freedom at this point are nuclei, not strange quark matter. So this is highly problematic for the model of constant back parameter, and so this is why we're motivated to change the approach and insert density dependence. So let us move on to the second case, where we have a density-dependent back parameter. As once again, we can explain observations, but as you can see for the 2 cases here, actually here we use 2 different values for the coupling constant of the repulsive interaction. In each case, the two solar masses constraint is easily satisfied. And if we revisit the previous plot, one can see that we can achieve higher transition densities at this point. As you can see also, as the stiffness of the hadronic phase increases, the maximum possible value for the transition density that allows for the explanation of the HESS constraints also reduces, which is problematic, and it's actually a good insight derived from this study. And also, as the strength of repulsive interaction increases, the maximum transition density also becomes lower. And actually, as you can see, the purple constraint, which is the highest mass pulsar ever observed, with a minimum mass at 1 sigma at around 2.18 solar masses, actually seems like it poses very strong constraints, but it actually is a rotating pulsar. And if we include rotation in our general relativistic calculations, this contributes to the battle against gravity, and it allows for maximum mass prediction. So all of this data would be shifted into the interval of the purple contour if we include rotation in our calculations. And finally, there is a gravitational wave event which is very puzzling in terms of the phase transitions we're studying. And this is the GW190814 event, which actually involved a compact object of unidentified nature with around 2.6 solar masses. Obviously, none of the equations of state that we have predicted in this study can reach such high mass. And we wanted to investigate a possible scenario of explaining it with our equations of state. So what we did is we employed a general relativistic code for extreme rotation, And what we found is that for the case of the strongest repulsive interaction, our equations of state can in fact pass through that region. But we have to make the assumption of extreme rotation. So briefly, with the concluding remarks, actually the reconciliation of both of these events that we have discussed is possible, but a strong phase transition is required in the neutron star interior. We saw that the constant value of B allows for the explanation, but there is a problem with reproducing large masses for neutron stars, and this problem seems to be solved when we are employing a density-dependent value for the back term. And also the puzzling gravitational wave event that we just discussed can only be explained under the assumption of Keplerian rotation. And what we do as the next step, what we're working right now, is that we aim to revisit this study, but instead of using scarm fractionals to describe the hadronic phase, we want to employ a microscopic relativistic approach. And with that, I would like to thank you for your attention.
The result from LIGO, the puzzling GW, etc., etc. Have you postulated any possible mechanism that might come up with that sort of extreme rotation?
Yeah, actually, in the literature, the main narrative about the formation of this object is that initially there was a three-body system with 2 neutron stars and a supermassive black hole, and the 2 neutron stars collided, forming this object. And it is when neutron star mergers occur, the object that is formed is expected to be extremely, to rotating at an extreme rate. And actually, the rotation that I'm showing here is uniform rotation. So we assume that the angular velocity has a uniform distribution. These objects actually are expected to be rotating differentially, which increases even more the maximum mass predicted. So this is a conservative estimation for the maximum mass if this is the formation scenario.
Are there any other questions, comments? If no, then thank you very much again. Next talk by Polychronis Koliogiannis about an event. I don't want to read these numbers. About an event and the existence of exotic matter, kaon condensation in perspective.
Okay, good afternoon. My presentation will be now about the existence of exotic matter and in particular kaon condensation in neutron stars in order to explain again the formation event, the HESS, which as we already saw, it has sufficient low mass and radius for a hadronic equation of state to describe it. We will start the presentation with a brief introduction about the exotic phases and emphasize to meson condensates. We will follow with the kaon interactions and reach up to equilibrium conditions and thermodynamical relations that are mandatory for the neutron star matter. And afterwards, I will present some numerical results based on an equation of state, and I will close with some remarks and hints for future work. Now, it is known since 1960s that with increasing density above the saturation density, the matter can undergo phase transitions to states that are different from the one at the saturation density. These states are called exotic states from a point of view that are different from the terrestrial nuclear physics. The existence of exotic phases are due to the strong interactions, such as meson condensates, and also the quark structure of baryons, as we already saw. There is also a mixed phase where two states can actually coexist. Now we will focus on meson condensates, and the particles to be considered are the pions and kaons. Pions are the lightest mesons and could replace the electrons as a natural candidate for condensation. Their appearance is at around the nuclear saturation density, and as a result, they soften the equation of state. Moving on to kaons, which is the main topic of the presentation. Kaons are the lightest strange mesons, but due to their large mass, their condensation was not obvious. However, it was shown that the negative kaons can condense into a zero momentum state at around 3 times the nuclear saturation density, and also lead to a strong softening on the equation of state. This is also the reason that we believe that a kaon condensation can be a possible explanation for this event with this low mass and radius. Now our starting point from, for the kaon condensation is the effective chiral Lagrange density, which I will just focus on these highlighted terms that are the hadronic interaction terms that we need to constrain. The constants of hadronic interaction terms are determined by these 3 relations and actually provide the 2 out of 3 constants. But what about the third one? There is a large uncertainty related to this parameter, which is related to the strangeness constant of the proton and also the kaon nucleon sigma term. This kaon nucleon sigma term is actually an attractive interaction between the nucleons and kaons that drives the effective mass of kaons down with increasing density and allows for a kaon condensation. It is constrained between this range of values, and after that it provides the constraints for the A3MS parameter, where the first term corresponds to 0% of strangeness and the last one is up to 20% of strangeness. We are now in need to find a ground state for our system with nucleons, kaons, electrons, and muons. For the considered densities, the beta decay and inverse beta decay are taking place, and by assuming cold matter, which is our current project, we assume that the neutrinos that already generated have left the system, and the chemical potentials are given by this relation. Furthermore, if the energy of if the electron Fermi energy is greater than the mu mass, it is energetically favorable for electrons to convert to muons, and if the effective mass of kaons is sufficiently low in dense matter, then the following strangeness changing processes happens, and we establish chemical equilibrium according to this relation. To find an equilibrium condition, we need a fixed baryon number state, which includes the energy density of a nuclear model, in our case, a momentum-dependent interaction model, and the symmetry energy defined as the parabolic approximation, actually the difference between the poor neutron matter and the symmetric nuclear matter. To determine now the energy density of the ground state, we actually need to extremize the energy density with respect to the proton fraction, the chemical potential, and the amplitude theta, which is actually an order parameter for the phase transition. The above procedure now leads to these 3 thermodynamical relations that are solved numerically, and in order to produce the critical value for the kaon's appearance and the quantities above this value. After that, we can actually calculate the energy density and the pressure of the model just by summarizing the baryon, the kaons, and the lepton part. To study kaon condensation, we are also in need of an equation of state that contains hadrons. The parameters that we took under consideration are the slope parameter, the incompressibility, and the strangeness of the proton from values 0 to 20%. Here I will just present a case with a slope parameter equal to 80 MeV, and incompressibility at 240 MeV, and symmetry energy at 32 MeV, but all the cases present similar results. In these 3 figures, we present the 3 values for the A3MS parameter as a function, as a pressure versus energy relations. We can see now that as the strangeness constant of the proton is increasing, the threshold value for the appearance of kaons is decreasing. And also, it is clear from this figure that the transition from normal matter to a matter with a kaon condensation is a second-order transition. To see now how the kaons contribute to the pressure on an equation of state, we present here the contribution of baryons, electrons, and kaons to the pressure. We can see in all figures that the contribution of leptons is actually the same in all the cases, but there is a change in the case of baryons, where we can see that as we increase the A3ms parameter, the pressure of baryons is increasing, along with the negative increase of the kaon pressure. We will now focus on the highest value of the A3ms parameter as an extreme case scenario. We already said that this phase transition is a second-order phase transition, and we can see at the critical value that kaons appear, the pressure is decreasing rapidly, reaching to negative values. This is also shown from the compressibility at the threshold, which is negative. And as we cannot have this behavior in neutron stars, we employ a Maxwell construction in order to have positive compressibility. With a Maxwell construction, we also introduce an energy gap at around 400 MeV per fermi cubed, and which leads to the appearance also of twin stars. Now, going to the particle fractions, we can see that prior to the condensation, all the fractions are increasing functions of the density. But with the onset of kaon condensation, the net negative charge in kaon fields causes the lepton concentration to decrease or even extinct. And after some density, we also again have the appearance of leptons, and even in some cases the production of positrons. Another quantity of interest is the speed of sound, which must be casual up to the densities, at least the densities that correspond to the maximum mass configuration. And if we consider here with the blue color the equation of state with a kaon condensation, we can see from this figure that quickly exceeds the causality limit. So to avoid the casual behavior at high densities, we employ two approximations, a Maxwell construction to fix the gap, as we already said, and the speed of sound later, and also an early phase Maxwell construction to lower densities, and again fix the gap and the speed of sound. Now, summarizing the above constructions, we can see from this mass radius diagram the actual softening on the equation of state, which reduces the maximum mass from 2.1 to 1.8 solar masses. From the inner plot, we can see that the two approximations that we took under consideration have a insignificant effect on the maximum mass. And moving on now to the boundaries of this HESS remnant, we can see that the transition density is critically related to these boundaries, meaning that with lower values of transition densities, we have more branches of the equation of state inside the boundaries of the HESS remnant. So a kaon condensation could actually explain this remnant. However, there is a major disadvantage at the moment. The maximum mass constraints from observational data are not fulfilled, and this is something that we try to fix. So reaching up to the conclusions, we saw that the strangeness of the proton plays a critical role in the location of the transition density, meaning that with increasing values of the strangeness, we have lower values of the transition densities. The transition density is related to the boundaries of the HESS remnant, where for lower values of transition densities, we have more branches of the equation of state inside the boundaries from HESS. So a kaon condensation can be a possible explanation, but as we already said, the maximum mass constraints are not yet fulfilled. Some future work contains the work that we need to do in order to fulfill these constraints, and we have to make a Gibbs construction in addition to a Maxwell construction, or maybe try a hadronic equation of state that reaches up to 2.4 at least solar masses, so that the reduction of the maximum mass will still be in the observational data. And also, an approach is to use a relativistic midfield model with the help of our collaborators from HESS University. Thank you very much. The kaon potential is actually defined in this model with this A3ms parameter.
So it's constant, it's not density dependent, nothing to it.
It's actually constrained by this kaon nucleon sigma term from experiments, and with a relation with a kaon sigma containing the alpha 3, the alpha 1, and alpha 2 parameters that alpha 1 and 2 are already constrained. We have the values, possible values, for the A3ms parameter.
If there are no questions, thank you again. We'll go to the last part of this session by Vikiaris, which will talk about supermassive compact objects in relation to dark matter.
Ναι, τέρμα αριστερά. Ωραία. Πού ρε.
Για να το κάνεις full screen,
Όχι, το δικό μου, δεν έχω βάλει το δικό μου.
Αυτό το κλείνεις.
Κάτω.
Μα αυτό δεν είναι δικό του. Κλείστο αυτό.
Μισό λεπτό να δω ποιο είναι το δικό μου. Κάτω δεξιά. Δεν το βρίσκω εδώ. Α, καλά, εντάξει.
Να πάνε εδώ. Εδώ, όχι, στο βλέπω αυτό. Εδώ και εδώ κάτω κάπου λέει full screen.
Οκ, λοιπόν, ωραία. Okay, hello everyone. I'm Michael Vikiaris, PhD candidate from Aristotle University of Thessaloniki, and today I'm going to talk to you about a new kind of object that we came across with my professor, Mr. Charalampos Moustakidis, and then we started working with our colleagues in Prague, Mr. Veselski and Mr. Vlasios-Petousis. And I'm going to try to keep it short because I see you're all tired, so we need a break. So, without further ado, I'm going to break down the table of contents of this presentation. First of all, we're going to talk briefly about the dark matter. What is it? Well, we're going to do a brief explanation of the two-fluid model and how we work in order to insert dark matter to our equations. Explain the stability criteria, which is a very crucial component of this presentation. It was the most painful thing to find. Then we will explain the mass cap, what it is, and why it's of great importance. I will showcase the results that we have, and then we will do a brief discussion as a conclusion. First of all, what is dark matter? There's matter missing in the universe wherever we look. Okay, that's what astrophysicists claim, and we call it dark matter since we cannot see it directly through electromagnetic forces such as light, but we can see its gravitational effects. And astrophysical observations, as I show you in these pictures here, shows us that the ordinary matter is not accountable for, sufficiently accountable for the gravitational forces that hold the cosmic structures together or how they behave. For example, galactic rotation curves. We expect that the stars on the outskirts of a galaxy should rotate with a smaller velocity than the stars near the center of the galaxy. But as we see, this does not happen, and we give this component to something that we don't see, that we call it dark matter. And another example is the gravitational lensing effect, where we basically stand in a point in the universe, we look towards a very distant light source, and if in between there is a supermassive object, the trajectory that the light follows is curved, so we see multiple idols of the same image. And if we go ahead and count the visible mass of this super heavy object, we will see that it is not sufficient enough for this event to take place in such proportion. So there's something that we don't see, thus we call it dark matter. Now, once that we think that it is there and it exists, let's see how we work with dark matter. And there are two types of dark matter that we mostly work with. Fermionic dark matter, we have fermions, particles that follow the Pauli exclusion principle, and bosonic dark matter, where we have bosons, particles that follow Bose-Einstein statistics, okay, all occupy the same quantum state. And these are the two types of dark matter that lead to different conclusions, but we have to be careful on how we can interpret and how we can obtain differences between these types of dark matter. So, as I will say earlier on how we work for these objects, first of all, we need to define the equations of state for the two fluids, as I will talk later. Right? But for the ordinary matter, baryonic matter, we use the APR equation of state because it's the best. It is in very good terms with the observational data that we see today. And so that leaves us with the dark matter equation of state. For the dark matter equation of state, as I said, we have fermionic and bosonic. I have these equations that you see here on your screen. And fermionic dark matter forms other structures, bigger scale structures than bosonic dark matter. And you see that from the equations that are different. But one needs to be cautious because if we insert, you see that term over here is the interaction term. If we increase it, if we put a very strong interaction, we will see that all the other terms have become negligible, so we cannot obtain any differences between those we cannot distinguish between those two types of dark matter. So we have to be already careful on how we can interpret our results. Now, two-fluid model. First of all, simple neutron star is explained by the solution of the Thomson-Oppenheimer-Volkoff equations, the known differential equations of mass and pressure that, given an equation of state and by inserting as initial parameters the pressure in the center of our configuration, let's say of the star, and the mass in the center of the star, then we solve these equations numerically and obtain in the end a mass and a radius as our output. To be precise, we obtain a pressure, then we say whether this pressure becomes zero, we have the mass and the radius of the star. So how do we insert dark matter into these equations? First of all, we have to follow some simple steps. Define the dark matter particle mass, first of all, choose its mass, then choose the interaction between the dark matter particles, and we use strong repulsive interactions in order to create the objects that you will see later. And instead of the neutron star central pressure that we used as initial conditions, now we also need the dark matter central pressure as initial condition. And in order to create the MR diagrams, as my colleagues showed earlier, we need some kind of correlation between those two quantities, some kind of a fraction between those two. So now the Thomson-Oppenheimer-Volkoff equations become 4 instead of 2, each set for each kind of fluid. And basically with B, I note the dark matter component and with, baryonic component, and with X, the dark matter component. So basically what the two-fluid model does is that you have, it treats baryonic matter and dark matter as two separate fluids that do not interact with each other. And so we solve these equations numerically, and given both the equations of state of the two fluids, the baryonic equation of state and the dark matter equation of state, we can obtain, as I said earlier, a mass and a radius for both fluids. So now that we saw how we obtain these kind of objects, let's talk about the stability of these models. And it's very tricky and it's very important. Why? Because the simple neutron stars, the simple one fluid model, the stability is known and is very simple. For increasing pressure leads to increasing mass counterclockwise in the diagram, as we saw earlier. So the very peak of the MR diagram, as my colleague showed before, is the last, let's say, stable configuration. If someone takes this stability criteria as the stability criteria of the two-fluid model, this is going to fail. Why? Because the two-fluid model we have to work entirely differently, because now we have to work with a number of baryon and dark matter particles, as you see here, down here, and we can obtain the stability in the curves for the different equation of state and dark matter parameters by extremizing these quantities. So it all comes down to solving these equations. So for a constant mass, we build configurations, and we see where these quantities become maximum and minimum, local and maximum and minimum. So, so what do we do? What's the methodology that we follow? First of all, we initialize the dark matter particle mass, initialize the interaction, use a fraction for the dark matter component, and then we derive the MR diagram. And someone could do the points 5 and 6, as I said, at first, but it doesn't really matter. At some point, you have to check for the stability. So we have to find the desired pure dark star and slowly add neutral matter. What we do is that, differently from all other works in literature, we don't start from a neutral star and we insert a little bit of dark matter to see what happens if we get a halo or perhaps a dark matter in the core of the neutral star. We work the opposite way. We start with a pure dark star, and we slowly add neutral matter to create configurations and see which of these configurations are stable and can exist. So we keep the total mass constant. We focus on a mass that we want to work with. And keeping this mass constant, we change the pressures in order to see what happens with the number of particles. So we end up with formations that expand from tens to hundreds and even thousands of kilometers long, and to up to hundreds of solar masses, let's say. Depending on the compactness of the object and the contribution of the dark matter to the total mass, we can talk about compact objects or dark matter halos or even dark matter inside the core of the neutron star. In literature, as I said, many people work with halos and dark matter that falls into the core. We work the other way, and we want to see what happens here. And this is what we see here as an image of your understanding. And this is what we get from a physical point of view. We get the quantities, the pressure with the radius, that when it falls down, we see the radius of the star. So the mass gap now. One of the mysteries in our universe is the mass gap. And in nature, as you see here, the highest mass or neutron star is of around 2 to 2.6, let's say 2.5 solar masses. And the lowest mass black hole is of 5 solar masses. So what happens? Why doesn't nature want to give us configurations inside this gap? Well, this is the mass gap of 2.2 to 2.5, sorry, to 5 solar masses. And we have to understand how we can populate it and if it really exists. With the potential of the configurations that I showed you, that I talk about now, we can, in fact, see objects inside the mass gap, because we will talk about rather a visibility gap rather than a real gap. And we can create compact objects of 3 and 4 solar masses that are in the mass gap with an ordinary neutron star in the middle, in the center. So we see an ordinary neutron star of, let's say, 1.4 solar masses that is, in fact, the core of a bigger compact object that is inside the mass gap. So if someone sees in the universe something that is a neutron star of 1.4 solar masses, and it behaves abnormally, gravitationally, so you have to think, what's that? One possible answer could be these very configurations. And here are the results that we got. And you see here that we can, in fact, with the 100 MeVs particle and a very small interaction, receive a compact object of 3.8 solar masses, very big in radius, of course. And the neutron star could be a normal-looking neutron star. And you see here, this is the stability criteria. The dashed line is the unstable region, the solid line is a stable region. And this is very logical if you think about it, because we start with a dark star, the number of dark matter particles is at the maximum, and then we insert neutron matter. So it is logical that the neutron matter increases while the dark matter falls, but you will see these regions here that are the unstable regions. And one has to be very careful, even when inserting a little bit of dark matter, because you can fall into these instability traps, as I say. And we see that these configurations can, in fact, be stable. You see them in the stability branch. This is for the 100 MeVs particle. This over here is for a more massive particle. It's for 500 MeVs particle and a little bit stronger interaction. And you already see that the mass now becomes a little bit smaller and in the radius, but it is also in the stability region. So we need a relatively heavy particle, not so big, and but at the same time not so small interaction in order to receive this kind of compact objects in the mass gap. But if we go ahead and increase the dark matter particle mass at, let's say, 1.5 GeVs, we can see, and this is a typo, sorry, it's 0.03, not 0.33, I'm sorry. We can see that we can, in fact, get a compact object inside the mass gap region, you see, of 3 solar masses, but the very last stable configuration that we can receive is of 0.63 solar masses and 8 kilometers long. So we have to be extra careful because we cannot overdo it, and we will see neutron stars, of very small neutron stars, that we believe that they don't exist. So we have to be extra careful on how we can obtain this information. If we see an abnormal neutron star, we can in fact constrain the let's say dark matter particle mass and the interaction or the correlation between those two. So we can pose constraints on the dark matter parameters, and we have to be extra careful on how to interpret these results. So, concluding, the existence of, we proved that these configurations of compact objects with dark matter and neutron star admixture really can exist in the universe. We don't talk about a halo, but we talk about a dark matter component that can be in fact in charge. And the stability needs to be thoroughly examined and not slightly taken, because as we said earlier, if you follow the ordinary stability, let's say quickly, where this could be the stable branch, we would miss all this branch and this configuration that in fact it is stable, but with the ordinary stability model is not. So we have to be extra careful because it took me a lot of months to actually find the stability of these models. I haven't seen it in other literature. And gravitational effect is the most prominent way to see these objects. As you saw, neutron stars become compressed in certain situations, lower mass and lower radius, so we have to be extra careful. And we can, in fact, talk about the gap objects, and we can fill the mass gap region, and it could explain rather a visibility gap rather than a real gap that exists in the universe. And we have to put great care in the initial parameters of the dark matter, because they can cause problems too small of a neutron star, or even more. If we go ahead and see here, we have a pressure of 120, and here's a pressure of 70. And here we could also have, in very big pressures, other problems, such as causality problems. We have to be extra careful on how we can obtain these kind of objects in the universe. So I want to thank you a lot for this presentation. I want to thank my supervisor, Charalampos Moustakidis, and our colleagues, Mr. Velasquez and Veselski, for their incredible job. And I would like to thank you, all of you, for your time.
Thank you very much. Any questions for me? Please.
Thank you for a very nice talk. I love theorists because they can imagine all kinds of things that may or may not actually exist.
Yeah.
So
that's the most beautiful thing in physics.
yeah, and then you have experimentalists that hold your feet to the fire. So what would be the smoking gun? In the end, you referred to something where you found a condition that was stable that wouldn't be stable if there wasn't dark matter involved. I mean, what's the smoking gun that everybody would then say, aha, he's not crazy, it's true?
Well, first of all, we have to see something like that in the universe. We have to, from other observation of X-rays and gamma rays, let's say, we must see a neutron star that is ordinary, let's say, of 1, 2, 1.2, 1.4 solar masses, or even 2 solar masses, I don't care. But then I want to hope that that there will be gravitational effects, such from gravitational waves, let's say, that say that there's an object there, where our neutron star is, where this object is of, let's say, 3.5 solar masses or 4 solar masses, and this will not correlate between them. So you would have gravitationally a 4 solar mass object, while you see from other observations, different observations, that this object is of, let's say, 2 solar masses. So you have to start thinking what this is. It could be a binary object, a remnant, or anything else. I want to believe that this is a dark matter object. And and as I said, if you go ahead and here, let's say, this would be the stable region in the one fluid model. Over here is the instability region in the one fluid model. So you have to work with other methods, other criteria, in order to find these configurations in the universe. So
So if one found something where you saw the gravitational wave that said there was more mass,
Yeah.
but your traditional observations give you less light,
Yeah.
then it's a candidate. But it
Yes,
could
it's
also be
candidate.
other things you mentioned.
It could also be other things,
So
yes.
how do you differentiate again?
I don't have an answer to this. I must hope that.
Experimentalist question.
Yeah, that's an experimentalist question. Yes. Thank
Okay,
you.
just to help the discussion, just a small caveat. This is very nice model, but depends on where are you looking at the sky. There are areas in the sky at which the dark matter density is higher, so the probability to have these effects is higher. So more or less, they're just neglecting areas that you have voids of non-existing dark matter, and then more dense dark matter, and then when you see something there which shows all these features that our student presented, then you say, I saw something which doesn't obey the Roman rules, what is it? Or go back to our data. We saw something was just neglected because it's too crazy to be true, and then it could be revisited. And furthermore, there are now some recent results or recent questions of some papers. Some people claim that they found something which is in this mass gap. They have one companion who goes around something, but they don't know what this companion, what is it? They know this dancing, they see this dancing, but they cannot know what is this one. Give us a small little bit glimpse of light on this one, or hope.
Yeah, what I didn't mention, because I didn't have also time, is there's a map of dark matter in the universe, as there's the cosmic web, let's say, that you see where there are the galaxies and the stars. There's the equivalent of dark matter, and you have places that there's no dark matter whatsoever, so you would never find this kind of objects. You must be crazy to think that there is an object like that. And you have spots that the dark matter is too much over there. And if we see something there that it fits all the results that we have, and it's in a point with a lot of dark matter, so it's a strong indication that it could be. Yes. Yeah, we can discuss it later. Yeah. Yeah. Yes. Not that I can think of now. I cannot think of something now to answer you.